Good morning, everybody, and welcome to the last of the webinar trilogy on the topic digitalization, the art of the possible. I'm Samuele De Guido, Planning Manager for the Institute of Digital Engineering and facilitator of today's event. For the one who are not familiar with ID, the Institute of Digital Engineering, we are an organization that promotes the uptake of digitalization into the UK automotive sector, and that's to enhance productivity and UK competitiveness, ultimately. Through this webinar, we actually aim to demonstrate some of the possibility that digitalization can offer to meet this set goal. The proof of concept we are going to explore today is called aiR-FORCE, artificial intelligence for reliability-based feature optimization with driver contextual intelligence. It is an IDE-funded project, and it's a collaborative project between Jlr, who's leading the project, and the University of Bradford. It aims at harvesting data over the air update, creating data lake. So a sets of huge sets of data, which then will be used through a machine learning system algorithm to characterize the driver behavior, coupled with a physics-based model, and optimize the control strategy to eventually improve customer experience. And those are really important topics for us, for IDE, especially put in the context of the digitalization roadmap, which has been worked by IDE and launched at the end of March this year, where this is on behalf of the Department of Business, Energy and Industrial Strategy, the Automotive Council and the Advanced Propulsion Center. And where items like software, hardware interaction in the context of modeling and simulation, as well as augmented intelligence, in particular the coupling of machine learning with physics-based models, optimization, and the use of in-field data to improve the engineering of the system itself, just to cite some of them that will be demonstrated through this proof of concept, are actually fundamental steps towards an holistic approach in the product's service lifecycle to ultimately demonstrate the goal in growth of productivity and competitiveness. But before going into the details of the aiR-FORCE project, I would like to remind you some housekeeping rules that most of the people that have been with us in the past events might actually be familiar with. So in particular, by default, your camera and microphones are off. However, you'll be able to interact with the presenters during the Q&A session, which is going to happen towards the end of this event. For that one, there is a Q&A box on the bottom of your screen, so feel free to post your questions in that section. There's also a chat box, which allows you to interact with the rest of the attendee, as well as asking technical support to my colleague Saniva. I would like to remind you as well that today's webinar is going to be recorded, and recorded will be available on our website. And finally, there's going to be a feedback form in your browser, an Mentimeter feedback form. So I would like if you could spend a couple of minutes to give us your feedback on the webinar. Now, I would like to introduce you the people that have worked on this exciting project, on the aiR-FORCE project, and they are Dr. Emanuele Angiolini, who is modeling and simulation lead engineer at Jlr, Professor Felician Campian, who is Professor of Automotive System Engineering Reliability at the University of Bradford, and they will be the speakers of today. And they will be then joined in the Q&A session by Alex Doikin, who is a postdoc researcher at the University of Bradford. Emanuele, over to you. You are on mute, Emanuele. Sorry. It's all right.
Can you hear me now?
Yes.
Yeah. Okay. First, thanks a lot, Sam, and good morning, everybody. Let me start by introducing myself. I'm Dr. Emanuele Angiolini. I've been working for Jlr as a modeling and simulation specialist in the powertrain department for the last 4.5 years. So Jlr and digitalization. Well, the company has always been a pioneer in the digitalization of customers' fleet data. Back in the days, the business developed a centralized system, which is still in use, that is collecting one-off data from customer vehicles every time that a customer visits a dealer. And these real-world customers' data is extensively used for intelligent product development and fleet health monitoring. Lately, with data over the air technology, Jlr connected vehicles are continuously sending data to the cloud, so allowing engineers to gather very precious insights that are used to improve customer experience. So in order to make the most of this very precious data, in the last couple of years, we have been ideating, developing, and implementing a set of tools and methodologies that are aimed at coupling data from Jlr digitized fleet with different model-in-the-loop techniques. So the aims are, on one hand, to assess the whole fleet performance from a statistical point of view, and on the other hand, aim is also to be able to develop advanced control systems, as in the case of the aiR-FORCE project, and also to tailor the requirements of our product to real-world scenario in order to allow ourselves, let's say, to avoid corner engineering. So let me say, the aiR-FORCE project came, obviously, let me say, as a kind of natural evolution of this approach. As Professor Campion will explain in detail, what has been done in the mark of this project, it was to couple the expertise that I just described from Jlr with the expertise from a University of Bradford in machine learning and artificial intelligence. So the final goal is to develop an intelligent engine control strategy based on a real-world driving behavior. Last, before giving the floor to Professor Felician Campion, I would really like to express all my deepest gratitude to Dr. Peter Lin for his great job at managing this aiR-FORCE project. And as he recently decided to pursue other career opportunities outside Jlr, he cannot be here presenting with us, but I'm sure he has all of our deepest gratitude. Thanks a lot for your attention, and let me now hand it over to Professor Campion that will share the technical details of the project, and we'll be happy to answer your questions at the end of the presentation.
Thank you very much, Emanuele, and good morning, everybody. It's my pleasure to be here today and talk about this project. So I'm a professor of automotive reliability engineering and director of the Automotive Research Center at the University of Bradford. I'm going to take you over the next 25-30 minutes through this project. Having got an automotive reliability background, I thought it's right and proper to start by giving you a little bit of a background to automotive reliability, which also sets the background for this project. I'm going to then outline the work we've done on driver behavior modeling based on large data sets, and then look at the two case studies that we've done part of this project, one on the DPF and one on a PHEV, and then we're going to wrap up with the summary and conclusions. So first of all, a little bit of background to the Automotive Research Center at the University of Bradford. So what you have listed there is the research units and laboratories which make up the Automotive Research Center. In particular, this work is pertinent to two research units: the Engineering Quality Improvement Center, which was established in 1995 as a partnership with Ford initially, and then the Advanced Automotive Analytics, which was set up in 2016 in partnership with Jaguar and Rover to move reliability engineering into the age and methodology of big data. So what you also have there is I've tried to include some of the teams that the Bradford team that is part of this automotive systems reliability engineering group. So going back to reliability background, I'm going to start with a rather personal reflection. So I'm going to go back to 2000, which is when I actually had the first EPSRC funded research project collaboratively with Jaguar and Rover. The question at the time, as I put it there, is a powertrain reliability challenge, and it was a matter of customer correlation. What does 300 hours on an engine test, let's say, engine dyno test, what does it mean in terms of customer mileage on the public roads? So, of course, the work at the time was all related to try to correlate the limited, very limited amount of data logged from customer usage with data sources from all other areas: durability test track, rig test, dynos, lab test, and increasingly computer-based modeling. So there were quite a lot of interesting developments at the time, both in terms of key life tests and stochastic damage accumulation models and so on. But putting things in the background, when we started this project, there was some quite prominent research coming from the automotive industry, and the title of that particular paper from Tim Davis at the time with Ford, "The Fallacy of Reliability Prediction in Automotive Engineering Tells It All." So without going through details, one of the big problems with the automotive industry is that evaluating reliability in the field is very, very difficult, because we need to have information about noise factors. So those are factors that affect the performance in the field. And the problem with the automotive is that the noise space is actually very, very difficult to establish. There is the same from Tim Davis. There was a very, very nice and insightful comparison with other fields, and the point there is that nuclear and aerospace, while they tend to have much harsher noise spaces, they are a lot more they are not quite as varied and a lot easier to monitor. A lot of the work in the automotive industry has been around reliability improvement, which is very, very useful in the sense that what we need to do is to prove whether a design is better than others, and that can be done based on testing. And well, there is quite a bit of mathematical theory there, but it is quite easy to operationalize. The question is, what has changed over the past 20 years? So reflecting on that and looking at, let's say, not the whole 50 years which you see in this picture, but only the last 20 years, what we see is that the vehicles have become, and vehicle systems have become increasingly more intelligent, interconnected, now autonomous. So what this means overall is that our ability to get data from the vehicles and use that to evaluate reliability and then optimize the systems is now a lot better. So what's the 2021 reliability challenge? I think it's very useful to look at this from the point of view of the SAE intelligent vehicle health monitoring capability levels, which is guidelines launched by SAE only a couple of years ago. And what we see, and just as Emanuele has alluded in the opening statement, is that in the automotive industry, we routinely have telematics data and increasingly data over the air. So where the research challenges now focus is how can we move from limited intervention in the field, so moving towards more component level proactive alerts, integrated vehicle health management, and eventually coming to self-adaptive health management, which is what we would like to have with autonomous vehicles. So the key point here is that automotive industry is now very much a data-rich environment. We have quite a lot of data from design and development, manufacturing, use, and retirement, and we don't just have data from vehicles, we also have data from the smart infrastructure in where the vehicles operate. So the research challenge, looking at it from a narrow perspective, is and looking at it from the point of view of big data analytics is, well, how can we leverage this data-rich environment to address the uncertainty challenges through a comprehensive framework for integrated automotive system healthcare. So some of the work that we have done at Bradford over the past 5 years in the Advanced Automotive Analytics research laboratory have prompted us. So that's largely working with industry partners. So funded research through industry partners is to come with this concept of an automotive healthcare analytics factory, and the point there is to come with processes where we exploit the data rich environment from the automotive industry and process that in a systematic way, such that we come with diagnostics and prognostics, which is largely improving the operation of the management of the operation of the vehicles currently in the field. Very importantly, feeding knowledge back into design, so taking data from all the phases of the life cycles and augment the design phase with intelligence. And just to illustrate some of the examples, very briefly, one of the examples is warranty analytics, where we've used warranty data and diagnostics data. So the last ID seminar with Cortical and Ford have discussed a very similar problem and a very similar approach. And another example is where we've looked at engine test data visualization. So what is interesting here is that we have taken engine test data, which tend to be quite large data sets with over 4,000 variables typically, and we use a visualization approach, so synthetic images, and then image machine learning on pattern recognition on images is very well established and quite fast, and that enables us to identify similar tests very quickly, and from there extrapolate better predictions. And a final example, I thought it's useful to quote here. This really sets up the discussion that we will have in relation to the work we've done in this project, is looking at this particular field of predictive diagnostics, where we have machine learning applied to historic DPF operation data regenerations to come with a prediction with an external diagnostic that can be used to validate when a regeneration event can be initiated. So now, before the last thing to put in this background is really looking at what is looking at more precisely, so to say, what are the uncertainty challenges for intelligent vehicle health monitoring. So we can discuss this in a lot more detail, but in principle we're dealing with two main challenges. First of all is the diagnostic problem, which is establishing what is the current state, so present uncertainty as is worded on the slide. So why this is difficult in the automotive industry is because even though the cars are becoming more intelligent, there are a lot more sensors, there are still a lot of components, and actually it is virtually impossible to sense everything that we would like to monitor. And therefore the challenge is to use the information that is available for diagnostics. So that limitation of the sensing data that has a projects an uncertainty challenge. So to illustrate that, one of the case studies that we have looked at is looking at an oil pump, and we would like to predict the state of an oil pump. Well, it's not really economic to put a sensor on an oil pump, and therefore we need to intelligently use hybrid methods to come with diagnostics. What is also very important from the point of view of the uncertainty is the future uncertainty. So having established a diagnostic, looking at what is the prognostic, so what is the remaining useful life, and what sort of action needs to be taken in place, depending on how the system, how the vehicle is going to be used in the future is a major uncertainty. So here we illustrate two scenarios based on where we are at the present time. Depending on the way the vehicle is used, we might want to that will give different remaining useful lives, which might mean that we might have to take different actions. So future uncertainty, that comes from future mission profile. So driver, that's influenced by the driver, the driving behavior, and that includes things like duty cycle or mission profile. We can sum it all up as mission profile, duty cycle, driving styles, environmental uncertainties. And this really sets up the problem. In order to manage the systems in a predictive with predictive intelligence in the field, we need to have a good understanding of the behavior, such that we can have a good way of anticipating, using that predictive insight into our control strategies and algorithms. So this brings me, after this quite large background to reliability, but hopefully that's been useful to set up the context. It brings me to state the objectives of the project. And as Sam said in his opening to the project, what we try to do with this is to prove the use of AI-derived contextual intelligence and predictive insight of driver behavior to enhance real-world efficiency and reliability, based on a reliability-based approach to control feature optimization. So some of the ideas that prompted this proof of concept project were derived from academic research. So to say, the point of this project is to test and validate these proposed strategies with high fidelity and model-in-the-loop testing. So using industry standard model-in-the-loop testing to test these ideas and methodologies. So we have considered jointly with the team at Jlr, at Jaguar and Rover, we considered two case studies. One on an after treatment. This was a use case that we have previously done some work on. So we looked at the DPF regeneration. We've also looked at a plug-in electric vehicle, a PHEV energy optimization case study. So I'm going to first give you a bit of background to the driver behavior modeling, and then I'm going to discuss in detail, give you an outline of the two case studies. So driver behavior modeling. The approach that we've taken in the project is we've started with historic journeys. So we have quite a large sample of historic journeys. So the final validation of the methodology had historic data from over 200,000 vehicles over 12 months. So that's quite a large data set. And we looked at variables from the journeys, from the past journeys, to look at what are the best ways in which we can model driver and driving behavior. We classify those variables into, let's say, journey parameters or trip parameters, things like start time, day of the week, lag time between journeys, and so on, several features, as you might want to call them. And we also looked at some of the driver behavior characteristics. So the sum for historic journeys, that's quite easily summarized in things like vehicle speed, fuel consumption, driver duty cycle dynamics. So note that the information here does not include the GPS detail, so the actual detail of the trip. So we have looked at two methods of or two separate approaches at applying machine learning. So one is looking at deriving a machine learning predictive model for each vehicle in turn. And in there, we've looked at three types of machine learning models. So we looked at classification. So for example, we can classify trips based on features. So long trips, short trips, long duration, short duration. Classification can be binary or can be multi-class. We then looked at we have looked at using hidden Markov modeling to predict the expected sequence of trips, and we've also looked at smooth PDF, multivariate probability distribution function, so using a Gaussian kernel, and it's not very clear from these two small pictures. This illustrates just two of the vehicles, the models for two of the vehicles, but what you see, this is just showing in a 3D plot shows the probability versus mainly the journey parameters, start of the day and trip distance or trip duration, and what you can see, the one on top there is just got two peaks, so that's very likely a commuter, whereas the one on the bottom is got a lot more detailed pattern. So what we've also looked at is, well, can we actually cluster drivers based on their behaviors? The idea being that if we identify clusters, then the problem of intelligent control could be structured based on identifying the cluster and then some specific model for each of the vehicle. So this approach is very much still ongoing research. What I'm going to illustrate here in terms of the quality of the models, I'm going to illustrate the classification models, because those are the ones that we have tested most extensively with within the two case studies with the high fidelity models. So first of all, just to give you a little bit of detail of the accuracy of the model. So normally we're looking at the outcomes in terms of true positive, true negative, and true positives, false positives. So generally we look at precision and recall. One thing to note here is that given that we're looking at quite a large number of drivers, and driver behaviors or trip behaviors from the driver can be significantly varied, the imbalance in the data is variable across the units that we model. So if we actually want to compare the how good the models are between different customers, looking at an accuracy measure like F1 or F beta in general is not useful. So F1 is useful with measuring accuracy with imbalanced data, but because imbalance can be very, very different across the whole volume. What we've chosen to do is to look at a simpler accuracy measure, which is shown here: true negative, true positive, plus true positive, the average of true negative and true positives. So on the right hand side, what we're showing here is for a smaller sample of the data, is looking at what is what sort of modeling accuracy we get. And remember, here we're looking at modeling each vehicle. So we had 1 year of journeys for each vehicle. So obviously we have used part of that 1 year for training and part of it for validation. So what we see is that the vast majority of the drivers can be we can derive quite good models that would be useful for optimization. What can be said is that some driving behaviors can be learned very, very quickly, so literally within tens of journeys. whereas others could take a lot longer, and that also reflects reality, not just in terms of the types of journeys, but perhaps different multiple drivers driving the same vehicle and so on. Remember that we have done all of this just based on the data that was logged in from the ECU with no information about the trips or the drivers. So let's see now, how do we use this information in this driver behavior modeling in some case studies. So I'm going to start first with looking at diesel particulate filter, just giving you a little bit of a background. So a particulate filter is there to help with meeting emission legislation. So the particulate filter traps soot particles. If the filter is doing a good job, what that means is that over time the filter will clog up, so will accumulate particles, and it needs to be regenerated. So we need to regeneration typically involves increasing the exhaust gas temperatures such that the particles are burned. So what you see here is some typical cycles of regeneration, and what you see is soot accumulation and then the regeneration of the filter. Now, this problem, if we're looking at it from a reliability perspective, we can look at the soot accumulation as a damage accumulation process. It's not proper damage because doing soot accumulation is doing the job, but we can model it as an cumulative process. The damage element comes from the fact that as the soot filter is getting loaded, it induces back pressure, and that affects the effectiveness of combustion. So we can model this as a state-based system. So the initial state where is empty, partial load. There is a full load state when we need to carry out the regeneration. The thing that we're looking here is the mass flow. Of course, if we don't have a successful regeneration, so what does it mean? Successful regeneration is return to the empty state. Repair is never perfect. So sometimes we have interrupted journeys. So short journeys are in particular a problem where the regeneration is not complete. And if a critical level of soot is achieved, that what follows is a managed DPF regeneration. So as I was saying, from a reliability point of view, the repair is not perfect. Okay, and we have multiple ways in which this is not perfect, but treating this as a reliability repair model, we can add a cost to the regeneration, and that cost can be sort of equated in CO2 emissions, but we can also take into account constraints or elements of cost function looking at reliability. So ultimately service interval and things that matter to the customers. So the objective here is to develop and validate an alternative control strategy to better manage or minimize the cost of the DPF regen. So what you see here, without going in detail, but is the derivation of a cost function based on the phenomenology and duration of the processes. So as I was saying, I'm not gonna go in detail. If we look here, what is the proposed intelligent DPF strategy? What we're looking is to use the machine learning driver behavior model, which is fitted based on the offline data. So based on the history of the driver, we fit a machine learning model. So we use a classification model, and then applying this in an online control fashion. What this implies is that we have a trip predictive model. So when a new journey is started, we can predict whether the journey will have the right parameters for sustaining a regeneration, and based on that, we based on the prediction of the regeneration, and where the current diagnostics, which is where we are, in which state we are with the DPF, we can change the strategy and basically only attempt to regenerate if the predictive trip meets the condition. So here you see a revised state-based model to reflect the assumption for the strategy. So in terms of the validation of the strategy, we have used this in conjunction with data over the air this time, and that is with appropriate density of the records to fit the model in the loop simulation. So looking at some results, so what we have here is a strategy validation of 900 customers. So we had the detailed historic. Well, the data was actually the simulation was performed by colleagues at Jlr on the model in the loop simulation. So with 900 customers based on unseen journeys, so we have 12 months in total. 9 months were used for training, 3 months for testing, looked over 24 months, such that we get a longer term prediction. What we see here is the result, and what the results mean. So we compare this with the baseline strategy. Okay, so the baseline strategy is you attempt regeneration when you hit a certain level of loading of the DPF. So what we see is that overall we've seen a 50% reduction in interrupted regens. So that is what that means is 82.8% of the vehicles saw an improvement. I'm quoting this in terms of the interrupted regen because that's easier to understand. In terms of the cost function, is a metric that would be a lot more abstract. So of course, with a composite strategy, we can use confidence predictions for our model, and we can further improve on this in the deployment of the strategy. So for example, where we don't have a good enough model, we can use the standard strategy. Moving on to the second case study, which is a plug-in hybrid. What we looked with a plug-in hybrid is again using the driver behavior model without GPS information to reduce to optimize the amount that the EV mode is used, and conversely reduce the amount of the use of the IC engine. So what this slide is, this is just for one vehicle, and is the history of the trips. What we're really looking at is that a lot of the vehicles would have quite a lot of repeat trips, and why this approach to driver behavior modeling is useful is because GPS information might not always be available. So the idea is very much similar as we looked previously. If we model the driver, if we have a driver behavior model in terms of trips, when we move into the online using current data. So we looked at the current journey parameters. We have a predictive distance. So distance is the simplest thing that we can use, but that can be replaced by quite easily by using different features. So we can, the best thing is to look at what is the predictive energy required for completing that journey. Of course, we within the model in the loop simulation, we have to take into account the current state of charge and the battery discharge model, and that would enable us to complete the simulation and evaluate whether an EV mode only journey is possible. So taking this strategy, with insight from predictive driver behavior. You have here some simulation results. Now, I just have to say from the beginning that there have been some quite mild assumptions taken into the simulation. So we've assumed, because we've assumed that that there's been overnight charging, and of course there is a trade-off if we attempt to run the vehicle in EV mode only. That implies a trade-off from the point of view of the driver in terms of reducing the max power available. So, however, under these assumptions, which are quite limited assumptions in relation to a real-world application, this is meant to show the potential, in particular with this case study, to show the potential of this strategy. So what you see here with modeling the loop validation for 10 customers over 12 months of simulated driving is just stating the conclusion. So these are 10 vehicles. What we see is that the potential is quite significant. So it's been possible to reduce the engine running time by 50 to 88% across the fleet. So that means a lot more journeys can be completed in electric vehicle only. Again, that is based on the assumptions that were stated on the previous slide. So, however, this is quite promising, and the key point here is that this all of this has been done with predictive driver behavior without using GPS information. So this brings me to the final to the wrap up of the work. So I'm gonna summarize the outcomes. So case study 1 showed that the intelligent DPF control strategy that demonstrated improved performance, significant improved performance compared to the base strategy, and that's been validated with high fidelity modeling the loop testing and customer data, so meeting the stated expectation. Case study 2 again showed significant potential for performance improvement. Both of them, both case studies, it's not just the CO2 improvement, but also the reliability, and in particular in relation to the service interval are important consideration. And one thing important is that there is as outcome, there is now a validated driving behavior modeling methodology, something that is tried and tested. We have also looked at what is the cost of these models with a view of possibly implementing this in real time, and chosen for the validation models that would be suitable for deployment, such that we have a meaningful testing. In conclusion, contextual intelligence and predictive insight based on driver and driving behavior without reliance on user and GPS user data and GPS can provide significant performance and reliability enhancement in a much cheaper and safer way, and closer to implementation or close to implementation. And finally, I thought it's useful to end up with a reflection, which I put it as lesson learned, and that is that this proof of concept project was delivered in less than 3 months. We've only started, we only had the go ahead for the project early in January, so and the project ended at the end of March. So that was less than 3 months. So it was not without challenges yet. Quite a lot has been achieved, and my reflection there is that the resilience, resourcefulness, and agility of the joint Jlr and UOB teams is ultimately what made the art of the possible for this project, and to me that's an important lesson learned, and I'm immensely grateful to the team, both the team at Bradford, but also to Emanuele and Peter Lind, who have supported the project and done a lot of the work at JLR in a absolutely fantastic way. Finally, as I'm saying, thank you and open up for discussion. I just want to say that we are organizing an engineering data and model-driven analysis at the UK Computational Intelligence Workshop. We will be sort of presenting some more technical details there. So those of you that would be interested, please join us. I know that the IDE will also support that event. So that's me. Thank you very much. Look forward to your question and discussion.
Thank you, Felician, and thank you, Emanuele, for before. As you said, yes, Felician. Thanks for sharing the lesson learned. It's been a short project, but great project with some challenges, which this one, together with the others one as well, with Wave AI Optima, has demonstrated how agility can produce very quick results and very insightful results. It's also great to see the accelerating pace that you described, in which the reliability can be increased through feedback of data to engineering team, and the opportunity to connect the software to the vehicle effectively for a more agile type of approach. You referred to test and validation as well with model in the loop. The other another nice things is actually the common methodology based on digital tech can be deployed for different use cases, as you demonstrate through this presentation, for short-term gains like the DPF, but also for a longer type of approach for electrified vehicle. So thanks for that, for both of you. Now we go into the Q&A session, and there is already some question coming in. If you, San, you'll be able to bring the people that have asked the question on. And they can ask the question themselves. I think we have Peter.
Hello.
Naveen, sorry.
Sorry. Hi, how's it going? Really great project there, Felician, incredibly detailed, and it's brilliant to see the benefits being realized so soon as well, obviously to JLR. I suppose my question, and not knowing too much details on the project either, and just sort of seeing what you've presented there, some of the machine learning techniques you use are really interesting. I'm assuming there's a lot of dimensions to the data that you've received, and there must have been quite a lot of work gone on into feature engineering it and cleaning the data for your model selection. And there's a lot of domain expertise, certainly that from a data science perspective, and also from an engineering perspective that has come into play here. Did you consider using principal component analysis to sort of reduce that dimensionality of the data? That's the first question. And secondly, I was just going to ask as well, in terms of visualizing the data for, better interpretation for someone that's not so technical, so someone at a management level, I suppose, is there techniques out there that can be used? Because although you've presented really nicely and you've really explained it really well, I assume that, it can be quite confusing trying to visualize and look through this data.
Okay, thank you, Naveen. So first of all, to say that the size of the data that we've looked at here is not that large in terms of the number of sensors or the number of columns, so to say, variables. So we have looked both with the preliminary driver behavior modeling. We looked at journeys available over a period of time. So you summarize that in terms of a fairly limited number of variables. Now, of course, you can start to look at by the time you start to look at features and extract features of interest, then that number goes up. But it's not that huge as it would be to look at the ECU data as such, or an engine test data as I referred. So the number of variables are not that large, so 10 to 20. Let me put it that way. And even with the online for the strategy, yes, of course, there you have a lot more variables. But in terms of modeling the driver behavior, you still have a reasonably small number of features that will go into the model. So of course, we're not shown the cleaning of the data and so on. So I just have to say that a lot of the actual data processing was done by the team at Jlr, the larger data sets. We have looked at a lot of exploratory data analysis and visualization, and that's something that you always do part of the course. So PCA was given that so dimensionality reduction wasn't I wouldn't describe it as being a priority, given that we're talking about a reasonable low number of features. But we have done quite a lot of cluster analysis and cluster visualization. So visualizing the data. Now, yeah, it's difficult to show. So in this presentation, we emphasize the final models, emphasize the models and how they can be used to optimize the features. But yes, in terms of visualization, I think there are a lot of tech tools and techniques out there that are available. I wouldn't say that we came with anything new or clever part of this project. We're very much focused on extracting models that make sense and are robust from the point of view of optimization.
Brilliant, cool. No, it's really nice to see the project, and really nice to see you know, sort of machine learning being applied more and more and delivering results as well. You know, demystifying the uncertainty and uncertainty of it all. Brilliant. No, thanks, guys.
Thank you,
Navin. Thanks, Felician. I think we have another question from Peter, who can come live now.
Yeah, thanks, Sam. Can you hear me okay?
Yes.
Yeah, just I'll try and keep it brief. I think at the start of the presentation, Felician talked about key life testing.
Yeah.
And I guess historically, you know, we've sort of adopted this, I guess, one size fits all approach where, you know, we try and come up with this 95th percentile magical custom quality drive cycle. And I guess now we've got the ability to generate vast amounts of customer data and then model it. Now, does that give us an alternative way of validating product, and maybe our Jlr already working on along those lines, really, of, you know, getting away from this traditional approach and doing something not just more virtually but more intelligently on, not looking at the extremes of the use case, but potentially, you know, where are the majority of customers using the product, where to validate rather than just looking at the envelope.
I can.
So I'll say a few words and then pass it on to you, Emanuele, if that's okay. So first of all, because key life testing, I mean, I've done a lot of work on key life testing, and key life testing has actually got a very good basis, and that is really setting up a way in which you can compare designs. So a key life test is not necessarily taking it to the most extreme, but is developing a reference over which you can sort of test designs. Now that reference is usually set up at the 95th percentile customer. I do believe that by using data we can do a lot more smarter validation. Now I'm going to hand it over to Emanuele to comment on that.
Yes, thanks a lot, Felician, and thanks, Peter, for your question. That is one of the methodologies that we are extensively working on, actually currently in JLR. What has been done, I can share a slide which will make everything easier, let's say, to follow. Is my screen live now, or?
Oh, it is.
Is it?
Yes. No.
Okay, so basically, what we moved on from, as Peter mentioned, is from testing or validating our product on a 95 percentile corner case, let's say. What has been done lately is develop a series of reference customers which come from the clustering of the whole fleet. So if we look at this case, for example, by only taking a couple of variables like average distance per trip and average speed per trip, we can cluster and associate to each cluster a specific weight of the fleet. So basically each cluster can represent a given percentage of the fleet. Internally, we have developed quite a lot of algorithms, let me say, that are allowing us to reproduce with fairly good approximation the driving behavior in terms of average speed of this set of customers, of representative customers. So what we do is we are able with these algorithms to develop, let's say, the behavior, the dynamics of certain important inputs for the simulation that can be exhaust temperatures or engine or oil temperatures and obviously vehicle speeds. And once we have this set of inputs created, we can feed them to use a model in the loop technique, a model in the loop tool that is basically then outputting, producing as an output the performance of the whole fleet in terms of distribution of when a service will be needed or any kind of this kind of information, let's say. Not sure if this answered the question.
Yeah, no, I think it does actually. And the fact that you had some slides already available to explain it, yeah, it does make it a lot more easy to understand. So no, that does. Thank you very much.
Thanks a lot for the question.
Thank you, Peter. And thank you, Emanuele, for expanding on this question. Looking at the time, in the interest of time, there are actually many questions coming in. Unfortunately, we might not be able to answer those now. We'll try to do that one after the webinar itself. We're collecting them, and we'll try to reach you after the webinar. I would say this actually brings us to the end of the webinar, as well as the trilogy of digitalization, the art of the possible. So I would like to thank all the attendees through these three webinars, in particular the one that are here today, as well as all the project partners that did work on this IDE-funded project to demonstrate what's the art of the possible in digitalization. And again, in particular, Felician, Emanuele, and Alex, they were here today. Also the rest of the team that organized the event, Sunny behind the scene, in particular, this one as well. I would say, just give a final reminder, all these webinars recording, as well as the digitalization roadmap, will be available on the IDE website. Having said this, I would like to thank you everyone again for attending, and have a lovely rest of the day. Thank you again.